show us American.
So
click with it after you put it in the belt. Click.
Yeah. Okay, can you hear me? Obviously.
Okay, well, our final speaker for the symposium, and by the way, after the symposium, I think we have a few minutes if anyone wants to linger and have a continued discussion. We can do that. But Henric Ostmark, visiting with us from Stockholm, DHS has had a long-standing collaboration with the Swedish government, with FOI and several agencies, and appreciate you joining us for this conference.
Yeah, it's my pleasure being here, so thank you everybody. I'm going to talk about standoff trace detection of explosive by Raman spectroscopy, and this is going to be for us a very interesting project because of every step we are taking. Everybody has said this is impossible, and if you're a researcher, it's really stimulating to do the impossible, especially when your colleague says no, you can't do that, and you show them that it's not that hard at all, or it's hard but it's rather fun as well. So FOI, it's the Swedish Defence Research Agency, or really we are calling the Swedish Defence and Security Research Agency nowadays, mostly. This is an outline of the presentation. I'm going to talk about the threat, a little bit of homemade explosives, the scientific technical approach and applications, and this is mostly about application. It's not about basic Raman theory. And then we have 3 examples of standoff trace detection or standoff detection technique. We do bulk, vapor traces, and particle traces, and then some conclusions. So, the first, since this is more about application of Raman techniques, I'm going to talk a little bit why do we do this. And we're doing this, we want to minimize the threat on the civilian and also the military society from improvised explosives devices. And the first questions we ask is, what are an IED? The biggest problem with them, they are unique. They are built from whatever materials are available. That means over time and place they are changing. And that makes it much more complicated than most other detection problems. What you can say is they always consist of ignition systems and explosives and normally a container. If it doesn't contain explosives, it's not an IED, and in this case not dangerous. Of course it could be biological or chemical warfare agents, but that's outside. So we are focused solely on the explosive, or precursor to explosive, I should say. So what do terrorists use? That's the first questions you need to ask. And I've just put up some example here. This is Oklahoma, 1995. It was a vehicle-borne IED. It was homemade explosives, that's ammonium nitrate and naphthamethane, and was approximately 2,300 kilos, and approximately 160 people was killed. We had Madrid, 2004. It was left behind IEDs on a train. It was stolen dynamite, EGGN or nitroglycerin based, and electronic blasting cap. And one of the most dangerous item ever invented, the mobile phone. You can use it to timing the bomb, or you can phone up the bomb. And then we have, it was about nearly 200 people died in that incident. Then we have London, 2005. It's person-borne IEDs, suicide bomber. It was homemade explosives. It was hydrogen peroxide as a fuel. You buy low concentrated hydrogen peroxide, you boil off water, and you get something that you can mix with the fuel. In this case it's for sugar. And then it was TATP or possible HMTD as an igniter. Everything was homemade. You can buy it in an ordinary store. In a few weeks you can make the bombs to cause that devastation. Then of course we had one in Stockholm. Unfortunately, Sweden was one of the countries that had suicide bomber together with UK and Afghanistan and Iraq. We also had to add Sweden to these things. It was very strange because people always said Sweden is never going to have this sort of threats. The first one, they have a bomb in the car. It didn't go, but the car just started to burn, and we got some people lightly injured by shrapnel from the glass. And then a few hundred meters away we have a suicide bomber. And as you can see from this target, it's about maybe 1 kilometer from the Royal Castle and for the Parliament building. So in the middle of Stockholm, in the Christmas time, we had a suicide bomber. And why do you need detection when it comes to suicide bomber? It's already done what you wanted to do there. Yeah, in this case, this is a rather interesting picture. This is from, all of the pictures here are from journalists that happen to be at the site. You can see the police car, you can see a dead suicide bomber here, and then you can see a lot of people standing here. And this is the next people, you can see it. Now, this is just a little bit like the time. You can see the police standing here at the corner. You have a suicide bomber here, and nobody's in the vicinity. People had realized, the police, that something was wrong, and you can see things on the ground here. This is the bomb, but you also can see a lot of unexploded bombs here, or parts. And you can maybe, it's a red bag here. And then, of course, you have the bomb squad examine the bag. This is the bag, this is the robots, this is the X-ray source, and this is the X-ray film. And this, of course, takes some time. In this case, we were very lucky. The only casualty was the suicide bomber himself. But if you have people that was hurt in the vicinity, are you going to save them with a lot of bombs? And in this case, it was about 12 kilos of unexploded ammunition in the vicinity of this person, in a total of 12 bombs. So if you really don't want to carry out rescue, so even in after incidents, you need to be able to do detection, and you want to do it from a standoff distance. This is a close-up picture of the police has realized this is maybe not that dangerous, and you can still see a lot of the parts of bombs here and exploded things. Then this summer we had an incident in Norway, or incident. We had this what we call lone wolf terrorists. He built a bomb, he detonated in the central part of Oslo, and about 8 people died, but you can see extensive damage on buildings. And this was in holiday time, and it was after office hour, so it was only 8 people. Have this been done in other time or not holiday, it would be tens and tens of people killed probably. And then you probably know that he also went away or shot a number of people in another place. 60, or I think it was about 60 people that was shot of this lone wolf terrorist. This was a car bomb. It was about 1,000 kilos of ammonium nitrate fuel. It was homemade booster and homemade igniter. So it's still viable threats. So terrorists use different explosives, and they use whatever they can get their hands on. That's the key point. It could be military explosives, commercial explosives, or today, unfortunately, increasing amount of homemade explosives. And that makes this detection business very much harder. So, some of the scenarios. This is a picture from a checkpoint in Iraq. This is a soldier standing checking a car. This is an other soldier. The second after this car explodes, it was a vehicle-borne IED. This soldier is instantly killed. This soldier lives. So in this case, the distance between life and death is about 10-12 meters, and that's why you really want standoff detection. This is another picture from Sweden. It's about postal robbery. After the robbery, the perpetrator, criminals, put some cars on fire, tens of cars, and then they put boxes that had bombs on them in different places in Gothenburg. And instead of hunting down the perpetrator, all the police could do was take care of these suspected bombs, but it took hours and hours to check the number of these bombs. And they only contained flour, and electrical wiring, but it still takes time to do this. Then, of course, you have wide area surveillance for mass transport and roadside bombs. You very much want to do that. These two scenarios, fixed checkpoints and suspicious objects, you can solve today. And I'm going to show you what we have done in this area. When it comes to prevention, you can do or damage reduction. That's how we can solve it. Military are very keen on damage reduction. They put armor plating on cars, they put protective clothing on soldiers and helmets and so on. You can't do this in the civilian society, or it's very hard to armor all the buses and subways and getting all the civilian people to wear helmets. So when it comes to civilian society, you need to focus on prevention. And you can detect explosive discharges, but probably more efficient is try to detect the bomb factories where the people make the bombs, because you have much more time. In a subway, if you find a person carrying a suicide bomber, you maybe have 1 second to decide, is this a suicide bomber? Are you going to shoot him or not? And as people realized in the UK, someone are incident. Building bombs today normally take days to weeks to months, so that's more efficient normally. You can also limit accessibility of related materials, and you have two ways. You have technical ways of doing this, and you can do it by legislation. I'm not going to talk more about that, but that's, at least in Europe, a very important step in this area. So, what we can conclude when we started this is better detection is needed. You need to detect many different substances. You need to easily adapt to new threats. You need high selectivity, reliable identification, reduced false alarms, rapid response, benign to non-human, better sampling of online or non-contact. But when we asked end users around Europe about this, what they really wanted, all people pick a number of those, but I think all of them said standoff detection. That's the key important factor. We want to do this from a safe distance. So, then of course, I just showed this, we heard it before. What is standoff detection? It means that the individuals and vital assets should be outside the zone of severe damage. That's both the operator and the equipment. So are the zone of severe damage? What is standoff? Is it 1 meter? Is it 10 meters? Or is it 300 meters? It depends on the application. If you check a letter, it's maybe 1 meter that is a safety distance, or 2 meters. If it's a suicide bomber, it's maybe 50 meters. If it's a car bomb, it's 500 meters. So you can't say a distance, it's depending on the application. We picked Raman spectroscopy for doing this. And the advantage is that it delivers energy to the target with minimal losses, and it gives substance-specific information. Unique identification, possible to build large databases, and possible to expand databases. The drawbacks to Raman spectroscopy is, of course, the weak scattered signal and fluorescence. And this was I think people said to us when we started this, you can't do this outside. You can't do this in strange weather conditions. You can't do this on long distances. Yeah. We have tested 3 things. Spontaneous Raman. It's good for the large amounts, bulks or spills. We are looking into resonance Raman. It's good for vapor traces, at least for some explosives. And we are looked into imaging Raman spectroscopy, which is good for particle traces. So just some examples now what you can do. This is the first experimental setup. We have a laser. It's a jug laser. It's pulsed, and this is important if you do this outside. And you have a gated detector. But otherwise, the ambient light is going to definitely destroy your Raman signal. We have a telescope. We have an edge or notch filter. We have optical fiber to a spectrograph, and we have a gated camera. And here you can see some of the equipment, and here you can see that we will have to do the testing. Nearly all of the testing is done outside. We keep the experimental equipment in a lab, and we do the testing outside in order to learn as much of this real environment as possible. The pulse energy we used to start with was 250 millijoules in green. This is, as you heard, not eye-safe. We have a frequency of 10 Hertz, pulse with 6 nanoseconds, and 532 nanometer. So this is laser, 6-inch telescope. This is from behind. We have the equipment inside in the lab here, and then we have the target about 55 meters away. In this case, it's a bottle of nifurmethane, and you can see it's lighting up quite nicely. This is some initial results. You can do it at 55 meter. It's very resilient. It doesn't really matter if it's raining or it's sunshine or snowing. You can look into bottles. It could be clear glass, brown glass, green glass, or bad samples. You get identifiable spectra in less than 1 second, and we have tested on nearly all explosives. This is just some of them that you can find, and as you can see, it's also homemade explosives, precursors, military explosives, civilian explosives. Then, of course, people said, 55 meters, that's okay, but you can't do it in longer distances. So we took out the equipment in a car in the forest. We put the laser, it's a little primitive, on an optical rail here in the backseat of the car. We have the power supply here for the laser, and just some stones to get the correct height. We put the spectrometer and the computer in the trunk of the car. We have the telescope. In this case, it's an 11-inch telescope outside the car. Then we put the sample across a lake in our site. It's about 100 milliliters of nitromethane in this case, and it's sitting in some bushes across the lake. You can see a bottle there. Oops. And this is the nitromethane spectra at 470 meters at 1 second. So you really can do Raman spectroscopy at long distances. This is just to show 1 hour. We did it a number of times, and one of the times we did this, it started to pouring down. So we could do the testing in good weather and in really, really bad weather. This is 1 second. This is ammonium nitrate, still 470 meters. This is for 1 second. You, of course, get better signals to noise if you do 10 seconds, but this is good enough, I would say. This is when it starts to rain. You lose some intensity, but you still get a good spectrum, and this is 10 seconds. So even in very bad weather, you can use Raman spectroscopy, at least if you have a green laser. The police asked us, in Swedish police, can we use this for detection in improvised laboratories? Can we distinguish between explosives, homemade explosives, and drugs? So we have a little bit hut, or what you call a shack, out here in the field. We put out still the laboratory equipment here. We use the bandwagon to transport it out. And here you see this telescope, and it's a primitive, and it started to rain this time as well. It's always rain in Sweden when we do field trials, it seems to. We put 2 grams of TTP drying inside this hut. We had a dual window, it's glass window, so we put the laser and the signal back through the window. Of course, we have optical path. This picture is really taken through the telescope that we use for doing the Raman spectroscopy. You can also get the picture. This is a close-up of the shack. This is really a copy of the Leeds lab where he really was making the London bombs. And this is the spectra of TTP. And of course, you can see this is a nice spectra. It was a 10-second acquisition time. And this one is good enough that you can hold as a proof in court to convict the people that this is homemade explosives. So, what about trace detection? Can you do trace detection with Raman spectroscopy? Yeah, we took a scenario. We said that detection limit at visual detection 30 minutes. We should do it in 5 seconds, and then we should see what is the detection limit with this equipment we have on ammonium nitrate, TNT, and DNT in this case. And we use algorithm for finding the detection limits. And we found that its for ammonium nitrate is 250 micrograms, TNT is 500 micrograms, and DNT is 370 micrograms. So the question is this enough if you want to do trace detection? What do we need? Yeah, first fingerprint of a bomb maker or something like that is probably in the order of micrograms. The fifth fingerprint, that's the 50th time after making the bomb someone puts the finger on something, it's about nanograms. So the difference between 500 micrograms and nanograms, this is really huge. So is this possible? Yeah, no, it's not possible with this equipment. We needed something else. So just to give you some numbers, 100 micron TNT particles is 1 micrograms, 50 microns in 100 nanograms, and the 20 microns is 10 nanograms. So this is what we have done so far. We had a laser illuminating an area with an optical systems that collects all of the light from this area to a spectrograph and camera for the detection. Of course, we can have very high focus, but then of course if you want to scan a large area it takes rather long time, and in normal we had between 1 centimeter and a few centimeter area. For the very long range we really used 30 centimeter by 20 centimeter area. So that means if you have a very small particle, normal particle of explosives is maybe 10, 20, 50 micron particles that you're looking for, and you're having illuminating area of about 30 millimeter by 30 millimeter. Of course, most of the signal is background. It's not noise, it's from the background. You also give signal from the background, and that's what makes this hard. And then of course you have very hard to getting the signal out of it. So what we came up to, what we have the same systems, we illuminate about 25 by 25 millimeter. We have the same optical systems, but instead we have a tunable Raman filter here. And then we have the same camera, it's an ICCD, it's 1000 by 1000 pixel elements. And then of course, explosive particle here, you get an image on the ICCD, because this is an imaging systems. And then you tune the filter to different sort of Raman lines. So this is our test setup. This is 25 by 25 millimeter. This is an optical picture. This is sulfur, DNT, ammonium nitrate, and TNT. This is ordinary Raman spectra from all of this substance. Green is sulfur, for instance, and so on. Then we take a picture, a Raman picture, from each of the some interesting wavelengths. This is 473 reciprocal centimeter. That's sulfur. This is ammonium nitrate. This is TNT, and this is DNT. As you can still see it is a little bit not that strong, it's much stronger here. This is just 4 wavelengths. We normally end up using 18 frames or 18 different wavelengths, and then we do reconstruction and use false color techniques. So this is a Raman image using false color techniques, and you can clearly see sulfur, DNT, ammonium nitrate, and TNT. This takes about 30 seconds to scan this area or take all the frames from this 25 by 25 millimeter. And of course you can use larger, but depends on what pixel or resolution you want. In this case we have resolution about 50 microns. This is some early field test. This was in France. We had some, not that small, but we used adhesive tape to put some samples on the steering wheel. The steering wheel from the car is from here to here, so it's still rather small. It's sulfur, ammonium nitrate, and TNT. And we measured at 12 meters distance through the glass window from the car, and this is what you get here. You can see that we have scatter, especially from the TNT. It ended up, we had too large energy in this case. We started to melt the TNT during the measurements. This is how it looks today. It's about 0.8 meter, just below 3 feet by 1 feet high. It's mounted on the pan and tilt head. Everything is mounted on this thing. We have a laser. This is a dial pump YAG laser. This is a power source from the YAG laser. We have a telescope. It's an 8-inch telescope. We have a beam splitter. We have a tunable filter. This is a tunable Raman filter, liquid crystal tunable filter. We have a CCD camera that takes the optical picture. We always get an optical picture at the same time as we get the Raman picture. And then we have the ICCD camera for collecting the Raman pictures here. For the moment, it's a 12-volt systems. We don't use so it's adapted for vehicle mounting. This is some picture of it. Here you can see it, and then we have a software. We have two cameras, one making a rather larger picture. This is about 75 centimeter by half a meter, and then we have a picture taken through the telescope. This is 27 by 27 millimeter, and you can see this is from the aluminum plate that we use for testing nowadays. So we did some testing. This is mixed particle in fingerprints. It's a aluminum plate, 27 by 27 millimeter, and this is the Raman ranked image. This is a sulfur particle. This is ammonium nitrate particles, and this is DNT particle. You can see this red one. The particles are a few milligrams to below 1 microgram, and you can do detection of particles below 1 microgram in this case and make it more realistic in a real scenario. We also did some testing. This is not color coded. This is just a ranked image. This is sulfur on a stone, and each of these red spots is a sulfur particle about 20-25 micron. That means 7 to 12 nanograms in size. So sulfur, of course, is a rather high Raman cross section, so it's easy, but you can do nanogram detection. This is done at 10 meters distance. We call the systems, of course, every system has a name. It's called Hlin, and that's the Norse goddess of constellation. And she's the one that lists to Norse mythology are going to protect soldiers in the field. So we thought that was a rather nice name for the systems. Okay, I'm going to talk a little bit very fast about trace detection in vapor. We heard that the most explosive doesn't high vapor pressure, and that's true. From the bottom here, the lowest vapor pressure, it's HNS, to the methane, it's nearly 20 powers of 10 in different vapor pressure. And of course, most of those explosives at HNS, ammonium perchlorate, HMX and TSP, you're never going to detect in vapor phase. But some of the homemade explosives or precursors have rather high vapor pressure are interesting for doing trace detection in vapor run. We opted for resonance Raman spectroscopy, did some tests. The resonance Raman means that you have a tunable source, that the excitation Raman line approaches an electronic transition line, and you enhances the signal strength and also make it more selective, and it makes it more complicated and more expensive. That's the trade-off. And the literature values said that Resonance Raman could be 100 and 1 million times enhancement. That didn't say compared to what. This is just the number you get in most texture. So we were interested to see how much can we actually get from explosives. We put up an experimental setup. We have a tunable laser. We have a chamber that we can control the concentration in. We have a UV telescope, optical fiber, spectrograph, ICCD, and a computer. We used a cross beam, so the detection beam and the excitation beam crossed. So we get a very nice signal. It's very small volume. It's only 5 cubic centimeters that we are probing, but that means we get rid of most of the strange effects. So it's the determination of the resonant enhancements, not to make the optical detection system. This was done inside the lab, I should say, not outside as most of the other stuff. We used the temperature to control the concentration, and we tested nitromethane, DNT, and TNT. This is some of the signal. This is the nitromethane as you get about 32,000 ppm. That vapor pressure at room temperature. It was very easy to find. You get a very nice strong signal here. If you use 232 nanometer laser. The 2,4 DNT, we use 263 nanometer. This is 1,400 ppm, and you can see the Raman signal. And TNT, this is 341 ppm, 248, and you get some nice signals here as well. This is the nitrogen. We use nitrogen atmosphere. Then we have the internal standard, so we can, and nitrogen doesn't have any resonance Raman in this area. This is for DNT. This is the UV absorption, and you can see that when we tune the laser, you get higher and higher or not absolute or relative cross section. This is where the optimum in absorption is, and you normally get a peak before that. This is the thing. Compared to 532, in this case we got a 45,000 times increase in Raman cross section, or relative Raman cross section. That's not too bad, I would say. We did some. This is the same for nitromethane. You get up here, and you get at 232. You get a nice Raman cross section. This is DNT. This is one of the techniques that gives you better performance when it's low concentration because of the self-absorption normally. This is 1445 ppm DNT, and you get about 1 to the -6 in Raman cross section. If you go down about a factor 10, you get 1 to the -5 in cross section, 10 times higher. So the signal strength is approximately the same, even if your concentration is lower. And that's because if you have too much concentration, you get self-absorption. We did some outdoor measurements. We had to heat the sample outdoor in order to get good signal because we have this just low energy, and unfortunately the laser is about, this case, 5 to 6 to 8 nanoseconds long. That means that the pulse is about maybe up to 2 meters long or something like that. And that means that if we want to focus across here, we need really maybe 1 nanoseconds or maybe 500 picoseconds. So we need a picosecond laser to do good real outdoor measurements. The results, enhancement for nitromethane, DNT, and TNT, it's about between 9,000 times and 240,000 times, depending on the concentration, I should say. So it's possible to measure standoff Raman spectrum vapor phase if it's high saturation vapor phase explosives, not HMX, RDX, and so on. I'll skip that one. I'll skip the fluorescence because go to direct conclusions. Normal Raman measurements can be used for bulk detection at hundreds of meters. Imaging Raman spectroscopy, huge improvements in signal to background. We get lower, much higher noise, but compared to signal to background, we get better. We can detect single particle with less 1 microgram, so I think we can improve this. And resonance Raman spectroscopy can be used for standoff vapor detection of high vapor pressure explosives and explosive precursors. The next steps we are working with is making it more eye safe, and that's by using a UV laser for the imaging instead of a green laser. We are on our way to building a 355 system, 355 nanometer systems for doing this. We have some problem with the filter in the UV range. That's the biggest problem for the moment. So I think that's the conclusion, and some acknowledgement. This is part of the group, and the rest that's not you see in the picture are mentioned here. We have a rather large group in Sweden working in this area. We got the money from Swedish Defense Material Administration. We have got some money for DARPA. We got some money from the Swedish equivalent to DHS. And we got a lot of money from the European Union for this sort of project. And I think I am here.
We've got all the time in the world for questions.
Yes, I have 2 questions. First one, I didn't understand why the Raman cross-section would be a function of the self-absorption.
It's not the absolute Raman cross-section, it's the relative measured Raman cross-section. And if you...
Okay, second question, could you say a little more about your filter for the imaging?
you mean for the imaging Raman?
Yeah.
We use for these measurements here, we are using a liquid crystal tunable filter. It has a bandwidth about 0.25 nanometers, and it's tunable between 500 and 650 nanometers. And it's very.
What will you use in the UV?
We are probably of optoacoustical tunable filter. That's what we are trying to implement for the moment. Or maybe a fabric pillow at alone instead, if we can get. If the problem is to getting a manufacturer to produce things like this, because it's on the edge of what you can manufacture. Otherwise, we have tried to use as many as commercial components for building this as possible. We don't want special components because it's going to be extremely expensive in such a case. More questions?
Looked at explosives on other surfaces like painted panels or plastics.
We have looked at glasses, car paints, plastic, leather.
Fluorescence is not a problem. Spot too.
No, not very much. You get fluorescence from some car paints. The picture I skipped in the end of this was how to do fluorescence suppression. We have done testing with a picosecond laser. It's made it much better. The problem with picosecond techniques today, you can't get a good picosecond detector. Even if the manufacturers say this is a 200 picosecond detector, when you really measure what it is, it's more like 800 picoseconds to 1 nanoseconds. So, but if you go in the real life, we really want to go to picosecond technique.
So what was the energy of your laser that you were using in imaging, the factory for imaging work?
200 microjoules per pulse, 10 kilohertz.
At 200 microjoules?
Yeah, 10 kilohertz. Now we are getting, it was not the optimum laser. We are now going to one that's about 2 millijoule per pulse, 1 kilohertz rep frequency. And the area we are illuminating is about 3.5 by 3.5 centimeter.
You're collecting a spectrum in each one, an image in each laser pulse?
Yeah.
You take 1 kilohertz or however many kilohertz?
Yeah, or we do what we call integrating on chips, so we don't read it out all the time. And the reason we really like this imaging is that we don't need to focus the laser. It means it easier to make it eye safe, because we have about approximately 10 square centimeter of laser energy instead of just 10 microns or something. And combined with what you do, having some other objects, this really can be an eye safe system. I think you had a question. Okay.
Any other questions? Speaking of eye safety. Okay, well, let's thank Henry for that.